Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson number 9 on Hypotenuse Leg. Hypotenuse Leg, HL. So what we're going to be looking at today is another one of these triangle congruence theorems. These theorems that allow us to prove that two triangles are identical, congruent, right, with limited amount of information. All right, and if it's not already obvious, hypotenuse leg is going to be a way to prove that two right triangles, triangles that have a right angle in them, are congruent. Okay, and we'll get into that in just a moment. Recall though, right now we have four different ways of proving triangles are congruent: side, 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 angle, side, angle, and one that we just recently saw, angle, angle, side. Today we introduce the final way. There isn't going to be another acronym in terms of proving triangles congruent, but today we introduce HL. So let's get right into it and see what it says. All right, hypotenuse leg. Let's take a look. If the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg of another, then the two right triangles are congruent. All right, so just to make sure that you get this, right, if I had these two right triangles and I knew that this 5, that these two legs were the same size and that these two hypotenuses were the same size, then I could say that these two right triangles are identical. They're identical. Now, it may seem that in hypotenuse leg, you only need two pieces of information: a leg equal to a leg and a hypotenuse equal to a hypotenuse. That seems a little bit strange given that all the other theorems need three pieces of information: side, 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 angle, side, etc. But if you think about it, and this is important, hypotenuse leg does need three pieces of information because truly you have to have a leg equal to a leg, a hypotenuse equal to a hypotenuse, but you also have to have a right angle in both of the triangles or they're not right triangles and hypotenuse leg can't be used. Now, the first exercise that we'll get into in a moment will prove hypotenuse leg. All right? So let's do that right now. Exercise number 1, the proof of HL. Let's take a look. In the diagram below, triangles ABD and CBD are given such that BA and BC are equal and BD is perpendicular to AC. Letter A, why does this fit the general scenario of hypotenuse leg? So we don't want to prove hypotenuse leg with a really specialized case. We want to make sure that this pretty much gets the job done regardless. So think about why this fits hypotenuse leg. Pause the video now if you need to. All right, let's go through it. So hypotenuse leg says we've got two right triangles, we've got a leg equal to a leg, and a hypotenuse equal to a hypotenuse. Well, what do we have? We know that BA and BC are equal or congruent either way, right? We know that BD is perpendicular to AC, so that gives us this and this as right angles. So I've got a hypotenuse equal to a hypotenuse, and I've got two right triangles. Why do I have a leg equal to a leg? Well, that's because they share this side. Now, I want you to understand something, and this can be a bit tricky, but it goes back to our unit on transformations and rigid body motions. If I had these two right triangles kind of separated, right, but I had exactly the same things marked up that I do now, I could transform one of the two triangles using a rigid body motion so that I matched up this common leg, this leg that's congruent. So I can always take two right triangles that have a hypotenuse equal to a hypotenuse and a leg equal to a leg and match that shared leg up so that I've got this picture. Okay, but let's write down why it fits the general scenario. It fits the general scenario because we have two right triangles. I'll just kind of abbreviate it like that. We've got two congruent hypotenuses, or hypotenusi. No, that's not right. Hypotenuses. And we've got two congruent legs. Remember, in a right triangle, you've got the hypotenuse, the side opposite of the right angle, and the other two sides are known as legs of the right triangle. Just in case you forgot that terminology from middle school geometry. Okay, we still haven't proved hypotenuse leg. We now want to go on and understand why this leads us to conclude that these two triangles are congruent. Let's take a look at B. Letter B. Why can we conclude that angle A is congruent to angle C? Angle A is congruent to angle C. Think about that for a moment. Hopefully you have it. This is actually from our last lesson. Okay? Our last lesson was all about angle, angle, side, and isosceles triangles. And one thing that we should note is that this larger triangle, triangle ABC, is an isosceles triangle with congruent legs AB and BC, which means that angle A must be congruent to angle C because the base angles of any isosceles triangle are congruent. All right? Anytime we have a triangle that has two congruent sides, the angles opposite of those congruent sides must also be equal in measure or congruent. Take a look at C. Are there any other angles in the two triangles that are equal? Are there any other angles in the triangle that are equal? This should be easy. Well, sure there are. In fact, I'll just say it right now. Sure. The right angles. Well, that's not a G. Let's try that a little bit better. The right angles. All right. So letter D now says, well, what theorem could we now use to prove, and let's bring this up, that these two triangles are congruent? Well, if you think about this, right? This is congruent to this. Okay. This is congruent to this. This angle is congruent to this. Forget about the shared side just for a minute, although you could certainly put it in. The plain fact is, we can now use angle, angle, side. We can angle, angle, side. All right? Because we've got two angles congruent to two angles, and then a side congruent to a side. So we go back to angle, angle, side. If you remember something from the last lesson, angle, angle, side then goes back to angle, side, angle. But no worries, because remember, once we prove it, we can use it. So what we've now proven, okay, because this can kind of get confusing in terms of the way all the logic gets nested inside of each other, is that we can take any two right triangles. If I have this right triangle and this right triangle, right? And I know that these two legs are congruent, and let's say I know the hypotenuses are congruent. Then I could take this triangle and I could match it up with that one, right? Ooh, that was nice. I could take this thing, let me group it all together. I could take this triangle, which isn't even remotely the same size as that triangle. I could match the two together, right, on that common shared side. Worst diagram ever. And then I could actually prove that the two triangles are congruent using angle, angle, side. Okay? So what that makes me understand, or what that gives to me, is that now I can say that if I have two right triangles whose hypotenuses are the same size, the same length, right, they're congruent, and I have a single leg of one right triangle that's congruent to a single leg of the other, I can now say that those two right triangles are congruent by HL. Okay? And we're going to use HL for the rest of the lesson to justify that two triangles are congruent and also to prove some other interesting results. So let's get right into it. That's just a horrible diagram. All right. Exercise number 2. In the diagram shown, AC intersects DE at B such that AC is perpendicular to DE. B is the midpoint of ED and AD is congruent to CE. Explain why B must also be the midpoint of AC. Okay, so there's a lot going on here, a lot going on. And what I'd like you to do now is take a few moments to mark up all the givens. Don't worry about what we're trying to prove yet. Just mark up what we were told in the problem is true on your diagram. Take a few minutes. All right, let's go through it. AC intersects DE at B. Well, nothing much there, such that AC is perpendicular to DE. Okay. Well, the fact that they're perpendicular tells me those two angles are right angles. B is the midpoint of ED. Be careful here. That tells me this is congruent to this. And AD is congruent to CE. Okay. There I've marked up all the givens that I have in this problem. Now let's make sure that we understand what the problem is asking us. It asks us to explain why B has to also be the midpoint of line segment AC. Now, a lot of times in explaining something, both in geometry and in algebra and other types of mathematics, you always kind of want to walk backwards in your thinking. And here's what I mean by that, right? In order for B to be the midpoint of AC, we really have to show that AB and BC have the same length. Okay? In order to show that AB and BC have the same length, what would be nice is to be able to show that this triangle is congruent to that one. And we have enough. So let's go through it. All right, I can say triangle EBC will be congruent to triangle DBA by hypotenuse leg because they are both right triangles and that's very important. Never use hypotenuse leg unless you know you have right triangles. They're both right triangles. Their hypotenuses are congruent. I don't know why I just put an apostrophe there. That's weird. Their hypotenuses are congruent, i.e. EC is congruent to AD. That was this given. And they have a pair of congruent legs. I.e., what is that? EB is congruent to DB. Okay? So those two triangles will be congruent by hypotenuse leg. Right? We've got the two legs congruent because B is the midpoint. We've got the hypotenuse congruent because that was given to us. And, very important, we have right triangles. So, right, now we know that AB must be congruent, that's here, right? AB must be congruent to CB by CPCTC. Our favorite reason, by CPCTC. So B is the midpoint, let me get rid of this, of AC by the definition of a midpoint. All right, that's it, right? It's kind of cool. Now, we could have easily done all of this in one of those T-table proofs. We could have. You'll see that I will kind of split my time evenly between paragraph proof and T-table proof. One of the things I like about paragraph proof, it allows you to be a little bit more freestyle with the way that you explain things. The T-table proof, it's really, here's my statement, here's my reason, here's my statement, here's my reason, right? Here, it's way more of an explanation, all right? But still, it has all the elements of proof. Anyway, take a look, write down whatever you need to, And then let's do a little bit more work with hypotenuse leg. All right, let's move on. Where's my advance? There it is. Exercise number 3. Now, a lot of times in geometry, things like hypotenuse leg aren't really important by themselves, but they're important because we can actually prove very important results based on them. And this is one of those problems. Let's take a look at what exercise 3 asks us to do. In the following diagram, CD is congruent to BD. I'm going to mark that up right away. CD is congruent to BD. And CD is perpendicular to AC. And BD is perpendicular to AB. All right? Letter A says, why can you say that point D lies equidistant from AC, ray AC, and ray AB? Why can you say that? Equidistant means the same distance. And why is that? It's pretty simple, actually. We can say that D is equidistant from those two rays because CD is congruent to BD, right? The plain fact is, when I measure the length from a point to a line, or a point to a ray, or a point to a segment, it's always talking about the perpendicular distance because that is the shortest distance from a point to a line. It's the shortest distance from a point to a line. So, since this is a perpendicular segment to that ray, and this is a perpendicular segment to that ray, this is the shortest distance from D to ray AC, and the shortest distance from D to ray AB, and those two segments have the same length, and therefore point D is equidistant from those two rays. But at the end of the day, it's as simple as saying, because CD and BD are congruent. You could also say because CD and BD have the same length, or you could even say because CD is equal to BD. I kind of like that too, because that is literally the distance between C and D and the distance between B and D. All right, now let's take a look at part B. It says prove that AD, ray AD, bisects angle CAB, and thus points lying equidistant from the sides of an angle lie in its bisector. So here's the important result. One of the kind of interesting results from hypotenuse leg is that you can prove that any point that lies equidistant from one ray of an angle, as it is from the other ray of the angle, must lie on the angle bisector, which probably makes sense, but let's now go ahead and prove it. And we're going to use hypotenuse leg. Okay? So, let's take a look. Ultimately speaking, what we're trying to prove is that ray AD bisects angle CAB. And actually, maybe take a little bit of time. Think about this a bit. All right, let's go through it. So, what does it mean for that ray to bisect that angle? What it means is that this angle, which I'm going to label as 1, and this angle, which I'll label as 2, they've got to be congruent. And of course, if I want to prove that two angles are congruent, probably my first choice that I should think about each time is to use CP/CTC reasoning. Now, how do I do that here? Well, there's only two triangles in the entire picture. If I can prove that this triangle is congruent to this triangle by whatever means, likely hypotenuse leg, then I can claim that angle 1 and angle 2 are congruent by CP/CTC. So let's take a look. Well, what do I know? I know that angle ACD and angle ABD are right angles. Okay, why do I establish that? I establish that because I need to claim that the two triangles are right triangles, right? Also, DC, I'll keep a CD. Also, CD is congruent to BD. And what is that? That's a leg, right, of a right triangle. finally, I just need those transition words like finally. Finally, AD is congruent to AD by the reflexive property and of course, AD happens to be the hypotenuse, right, of those two right triangles. So now we've got two right triangles, right? We've got a leg congruent to a leg. We've got a hypotenuse congruent to a hypotenuse. So let me come down here a little bit. Triangle ADC is congruent to triangle ADB by hypotenuse leg. Right? By hypotenuse leg, those two things are congruent. Right? Let me mark the congruent hypotenuses, that shared side. So, angle 1 is congruent to angle 2 by CP/CTC. And what would that then be? And then, ooh, that's interesting, red just coming out of nowhere. Goodness only knows. And ray AD, let's see if we can get random red to show up again, bisects angle, let's see, CAB, because angle 1 is congruent to angle 2. All right. Weird. Again, I couldn't do that even if I wanted to. And I didn't want to, which is why it happened. All right, so again, make sure that you understand what just happened, right? We knew on this angle, with this ray drawn, that this point on the ray was equidistant from the two sides of the angle, the two rays of the angle, okay? Based on that, and that alone, right, we were then able to establish that these two triangles were congruent based on the hypotenuse leg theorem. Because these two triangles are now congruent, we know that these two angles, which are corresponding parts of those two congruent triangles, are also congruent, and that means that AD must bisect this angle because those two angles are the same measure. All right? And again, this gives us a very important result in geometry, a very important result from geometry, which now maybe I'll actually go to red on purpose. All right, let me kind of summarize this. All points that lie equidistant from the sides of an angle lie on its bisector. All right. And again, it probably makes sense, right? Because if you've got some other angle like this, and you've got its bisector drawn in, then it kind of makes sense that that point, right, would lie closer to that ray, and this point would lie closer to that ray. Right? So it kind of makes a lot of sense that if I've got a point that's equidistant from the two sides of the angle, it should lie on that ray, that line, that segment, whatever, that bisects the angle. All right? Let me step out of the way, though, so that you can look at the reasoning that goes into this proof. Maybe I can actually get this thing to advance. Apparently I can't. There we go. All right. You can write down anything you need to. Take a little bit of time. All right, let's get it out of here. Let's move on. Okay, now for a formal statement reason kind of proof. This will be one of the more challenging proofs we've done so far. Okay, so what I'd like you to do is take a little bit of time with it for yourself. Okay, pause the video now, take as much time as you need or as much time as you're afforded if you're watching this in class, and try to think about how you do the proof. I've got the diagram up here. I've also got it reproduced down here. We're going to mark up the givens on both of them once you've thought about the proof for a little bit. And I just wanted the one down here so that as we kind of outline all the statements and reasons, you can see what's going on from both diagrams. Take a few minutes. All right, let's go through it. Now, again, it's your choice. Either start with what you're trying to prove and really understand what you're trying to prove, not how to prove it, just what you're trying to prove, or start by marking up the givens. I'm going to start by marking up those givens. I'm going to do that again in blue, so let's get rid of that. We're told that PQ is congruent to SR, so this is congruent to that. We're told that QT is perpendicular to PR. That means that this is a right angle and this is a right angle. That SV is perpendicular to PR, so a right angle and a right angle. Whoops. Okay, come on. And a right angle. And QT is congruent to SV. All right. Now that we've marked those up, let me again do it down here really quick. All right, so that we've got them everywhere. Now let's understand what we're trying to prove. Let me go over here, change to red, so I can highlight what we're trying to prove. We're trying to prove that PV, this, is congruent to RT. Ooh, that's not going to work well. This. Hopefully that works okay. Now, oftentimes when we're trying to prove that a segment is congruent to a segment, we're going to use CP/CTC reasoning. And we are going to use CP/CTC reasoning. But let's look for a moment why it's going to be a little bit more challenging than what we've seen in the past. You see, I want to prove that PV is congruent to RT. And so if you will, right, within this diagram you can tell that there are 4 right triangles, okay? In all likelihood, the 2 small ones here are congruent and the 2 larger ones here are congruent. I say in all likelihood because I haven't proven anything yet, okay? I don't want to assume something just based on what it looks like. So, given that we're trying to prove that PV is congruent to RT, it kind of stands to reason that we might want to prove this larger right triangle is congruent to this larger right triangle, and then we'd be able to say, all right, there it is, we're done. The problem is we don't have nearly enough information to prove that those 2 larger right triangles are congruent. In fact, on the right triangles all by themselves, all I really know is that that leg is congruent to, well, I don't even know that. Yeah, I was going to say this leg is congruent to that leg. Oh, I marked that up wrong there. Let me get rid of this. Go back to blue. My apologies. Right, SV is down here. Right, all I know in terms of the larger right triangles is that that leg is congruent to that leg and that they're right triangles. I don't, in any sense yet, know that a hypotenuse is equal to a hypotenuse, right? To use HL here, I'd have to have that the hypotenuse, which is down here, is congruent to this hypotenuse up here, and I haven't been told that information. The worst thing that you can do in a proof is to write down that you know something that you don't know. That's why you should always know what you know, and just importantly, know what you don't know. And I do not know yet that these 2 are congruent. But one thing that should be obvious, at least once you become comfortable with the hypotenuse leg, is that we have everything we need to prove that this little right triangle is congruent to that little right triangle. Now, what advantage would that give me? Well, if I could prove that this little right triangle was congruent to that little right triangle, then, let me switch to a different color, I could prove that PT was congruent to VR by CP/CTC, right? I could get that congruent to that. Now, why would that be helpful? Well, if I knew that those 2 little pieces were congruent, then I could do a little bit of an addition proof. by adding VT or TV, depending on what you want to call it. I could add TV onto both of them to prove that PV is congruent to RT. Whew, so this is fascinating because this is the first time we've kind of seen this almost exclusively when I've been trying to prove that two segments are congruent. When that's my final thing, then the reason for it is CP/CTC. That's not true here, right? What we're going to do here is we're going to first get out the given that we've got those perpendicular line segments. Now, based on that, I'm then going to say that this angle, QTP, and this angle, SVR, are right angles. I have to do that. It probably seems a little silly, but that's what justifies that I have right triangles. That's an easy enough reason. Perpendicular lines form right angles, or perpendicular segments form right angles, or whatever, right? This is all I need to establish that I've got two right triangles. Then I can say that PQ is congruent to SR. That's here and here, and those are the hypotenuses of those two little right triangles. And I can say that QT is congruent to SV, QT, SV, and those are the legs. Again, those are just givens, right? And then finally, I can say that those two little triangles, right, PTQ and RVS, are congruent by the hypotenuse leg theorem. Okay? So now I know that this little right triangle and that little right triangle are identical. And that allows me then to say that PT is congruent to RV. Again, let me just highlight that in green, right? The argument I just did was to build up to the fact that those two segments are now congruent. Okay, but I want this longer segment congruent to this longer segment. And I can do that by simply adding that TV segment in the middle, right? So I say TV equals TV, or TV is congruent to TV by the reflexive property. It's not showing up. It showed up earlier. We'll put it in right now. Oh, reflexive property. Where have you gone? By the reflexive property. Then I can add those two equations together with the addition property. And finally, I get what I want. Now, why can I say that PT plus TV is PV and RV plus TV is RT, besides it sounding kind of funny? That's because the whole is the sum of its parts. And that is, again, very, very different, right? I'm kind of used to the idea that this should be CP/CTC, and we did have CP/CTC kind of in the middle there. But I then needed to go on after proving two triangles were congruent and parts of those triangles congruent to do a little addition proof in the middle. All right. Let me pause for a minute before I kind of scroll up and we do the last problem in this lesson so that you have a little bit of time to write down this reasoning if you need to. All right. Let's take a look at the last problem. I left the last problem on here because it relates to the previous one. Exercise number 4. Given what we proved in, exercise number 5. Given what we proved in exercise number 4, explain how you could now prove that triangle QTR is congruent to triangle SVP. So this could make for an even longer proof, right? I mean, this could be a proof, that last one was 8 lines long? This thing could go 15 lines, all right? We'll see some in the next lesson that are pretty long. Hopefully not 15 lines long, but they're pretty long. So now the question is, how could we prove that the larger right triangles are congruent? Well, keep in mind what we know at this point, right? At this point, we know specifically about the larger triangles that those two angles are congruent. We know that. We also have just proven that this side is congruent to this side, right? We know that those two sides are the same, okay? And we were already given that QT was congruent to SV, all right? Now again, it's a little bit tricky to see this. Let me just draw QTR and bring it over here. It's nice to be able to do that. What do we know? We know this, this, and this, right? And let me do this, bring it over here. This is SVP. We know this, this, and this. So how can we now prove that these two triangles are congruent? Which of the major theorems does it? Well, hopefully it's obvious. We could now prove they're congruent by side angle side. All right, so you could imagine this proof up above being even longer, right? Where the final conclusion is just prove that triangle QTR is congruent to triangle SVP. This is where a lot of students find geometry proof quite challenging, because we would literally have to prove the smaller two triangles are congruent. Then we'd have to get those longer sides of the larger two triangles congruent using that kind of addition proof. And then it would be a pretty easy step to go on and say that the larger right triangles are congruent using SAS. In fact, it would only be really one more line. But it would be kind of hard to map all of that out. Still, there it is. All right, let's wrap it up. So at the end of the day, we've got a couple big takeaways from this lesson. Number one is simply hypotenuse leg, and we want to have that one in our tool bag so that if we come along in a situation where we need to prove two triangles are congruent, and we know they're right triangles, and we know their hypotenuses are congruent, and we know a pair of their legs are congruent, then we can say, okay, these two are congruent by HL, okay? And the other thing, and again, this could come up a little bit later in the course, is that any point which is equidistant from the sides of an angle must lie on the angle bisector. Okay, and again, we'll see that later on in the construction unit, which is next unit. Yay! All right. Anyway, for now though, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.